For over 50 years, the narrative of the universe seemed firmly established. It's a tale as familiar as it is grand, a tremendous Big Bang followed by 13.8 billion years of cosmic evolution, sculpting the universe into the intricate tapestry we observe today. This framework, known as the Standard Model of Cosmology, has stood as one of the most remarkable theories ever formulated in the realm of science. Then emerged the James Webb Space Telescope, JWST, a magnificent instrument engineered to gaze back towards the cosmic dawn and scrutinize the initial chapters of this epic story, seeking the birth of the very first galaxies, the building blocks of our cosmic neighborhood. What it uncovered, however, posed a profound challenge to this established understanding. Recently, Nobel Prize-winning scientist Adam Riess issued a stark warning. We may have fundamentally misinterpreted the nature of the universe itself. To grasp the depths of cosmologists' concerns, we must first delve into the elegant portrait they had meticulously painted, a masterpiece known as the Lambda-CDM model, or Lambda-CDM for short. This model narrates a coherent story that begins a staggering 13.8 billion years ago. At that moment, the universe burst forth from a singularly hot, dense point, embarking on an expansive journey across the vastness of space. For several 100,000 years, it existed as an opaque fog, but as it cooled, the primordial atoms, mostly hydrogen and helium, began to coalesce, rendering the universe transparent. The faint afterglow from this formative epoch, known as the cosmic microwave background, serves as a delicate infant snapshot of our universe, a cornerstone of Big Bang theory. According to the Lambda-CDM model, the following several 100 million years comprised the cosmic dark ages. The CDM stands for cold dark matter, an elusive substance presumed to constitute about 27% of the cosmos. This dark matter formed a gravitational scaffolding, enabling clumps of gas to coalesce under its influence. Gradually, gravity sculpted these gases into dense conglomerates, igniting the first stars that would eventually cluster together to form the primitive galaxies we now know. The model predicted these nascent galaxies would be small, clumped, and disorganized, the humble seeds of the majestic galaxies we see today. This theoretical framework has been astonishingly successful. It forecasted the patterns within the cosmic microwave background with remarkable precision and elucidated the large-scale structure of the universe. For decades, every observation appeared to resonate harmoniously with its predictions. Then, the JWST was launched. Designed to challenge this very origin story by probing the most ancient recesses of the cosmos, JWST dove into the depths of time. However, when it turned its gaze back to just a few 100 million years post-Big Bang, it revealed a startling revelation. Far from uncovering the small, infantile galaxies anticipated by the model, it discovered galaxies that were shockingly massive and remarkably well-formed. Some even exhibited mature structures, like elegant disks, which should not have had sufficient time to evolve. The bewildering aspect of this finding lies in the level of organization these galaxies displayed during an epoch when most were expected to be chaotic and unsettled. The timeline, it appeared, was profoundly awry. Interestingly, subsequent analyses have suggested that some of these seemingly massive galaxies are not quite as grand as they initially appeared. The intense luminescence emanating from actively feeding supermassive black holes at their cores might be inflating their size and brightness. Yet, even with these adjustments, a lingering issue persists. The early universe seems to harbor roughly twice as many massive galaxies as current models would predict. While these galaxies may not be impossibly large, their sheer abundance in the primordial universe remains perplexing. Finding an abundance of large, early galaxies presents a significant challenge to our current understanding of cosmic evolution. The Standard Model of Cosmology imposes a limit on the rate at which galaxies can form, dictated by the time it takes for gravity to accumulate sufficient gas, for that gas to cool into stars, and for those stars to synthesize the heavy elements necessary for complex structures. However, the galaxies identified by the James Webb Space Telescope appear to have surpassed these expected constraints, raising fundamental questions about our cosmic model. Renowned scientists have expressed their astonishment over these discoveries. John Mather, a Nobel laureate and senior project scientist for JWST, noted that the characteristics of these early galaxies are not quite like what we thought they were. He described them as surprisingly big, bright, powerful, and numerous, which deviates from the predictions made by the Standard Model. The situation is further complicated by the ongoing Hubble tension, a term that refers to the discrepancy in measurements of the universe's expansion rate obtained through two different methodologies. One approach, based on observations of the cosmic microwave background, suggests a slower rate of expansion, while another, which measures distances to nearby stars, indicates a faster expansion. Scientists had hoped that the JWST's advanced measurements would clarify this tension. However, the observations have only reinforced the existence of this discrepancy. Adam Riess, another Nobel laureate who co-discovered the accelerating expansion of the universe, has emphasized the implications of these findings. He remarked that the ongoing discrepancies prompt serious reflection on our understanding of the universe's composite and the underlying physics. Riess suggested that these developments open up the real and exciting possibility that we have misunderstood the universe. Such admissions from leading scientists indicate that our foundational knowledge about the universe's essential components may be flawed. If the expansion rate is indeed different from what we thought, it could imply that the age of the universe is also miscalculated. Additionally, if galaxies formed at a faster rate than anticipated, it may suggest that our theories regarding dark matter are incomplete. These anomalies do not represent mere inconsistencies. Rather, they point towards a deeper mystery that could fundamentally reshape our understanding of the cosmos. As our most trusted model begins to show fractures, the question arises, what comes next in our quest for understanding the cosmos? A crisis of this magnitude normally signals the onset of an extensive search for what scientists refer to as new physics. This pursuit typically follows three primary avenues. Possibility 1. We just need to tweak the model. This option represents the most conservative approach, suggesting that while lambda CDM, the Standard Model of Cosmology, may not be entirely flawed, it could simply be lacking in certain aspects. One possibility is that the earliest stars in the universe were extraordinarily massive, often termed population 3 stars, which could have catalyzed galaxy formation at a significantly accelerated pace. Another intriguing concept revolves around the existence of cosmic rivers, enormous, unseen filaments of cold gas that traverse the universe, providing essential fuel to galaxies and enhancing their growth rates. Furthermore, researchers are revisiting observational data with a fresh perspective, positing that the intense brightness from highly active supermassive black holes may obscure or contaminate the light emitted from some galaxies, resulting in their appearance being more massive than their actual mass. Possibility 2. The universe is not what we think it is. This avenue is far more radical and challenges our foundational understanding of the universe itself. The Hubble tension, a persistent discrepancy in the observed expansion rate of the universe, might offer significant insights. Some theorists have speculated about the influence of a form of early dark energy that would have provided an additional impetus just after the Big Bang, accelerating galaxy formation in its infancy before vanishing. Additionally, we must reassess our fundamental assumptions regarding dark matter. Traditionally thought to be cold and slow-moving, what if its characteristics have shifted over cosmic time? Adam Riess has articulated the importance of determining the expansion rate, which could elucidate whether dark energy is a constant influence or something that evolves, a groundbreaking revelation with profound implications. Some scientists are even investigating the intriguing theory that our galaxy resides within a vast cosmic void, which could result in an accelerated local expansion of the universe, making it seem swifter than in other regions. Possibility 3. We need a revolution. The most speculative option suggests that what we truly require is not just an adjustment to our existing model, but a complete overhaul of our conceptual framework. This embrace of new physics invites innovative thinking and radical ideas. What might this entail? Certain researchers have highlighted these emerging observations as potential validations for alternative theories of gravity that modify or extend Einstein's general relativity. Such theories might account for cosmic acceleration and rapid galaxy formation without relying on dark matter or dark energy, fundamentally altering the landscape of cosmological science. Moreover, there's the profound notion that the universe might be older than current estimates suggest, providing a solution to the troubling timeline discrepancies. However, this would introduce a host of new conflicts with other established measurements, posing significant challenges. Amid such crises, though, the scientific community recognizes that no idea is too outlandish to reconsider. Adam Riess himself has expressed optimism, viewing this conundrum not merely as a challenge, but an unparalleled opportunity for breakthroughs in our comprehension of the universe. We find ourselves in a defining moment for the field of cosmology. The James Webb Telescope, JWST, a groundbreaking instrument designed to unravel the universe's mysteries, has instead unveiled complexities that challenge our existing paradigms. The unexpected discovery of a wealth of surprisingly mature galaxies alongside the persistent Hubble tension has led science to a pivotal crossroads. The cautionary insights offered by Nobel laureates should not be interpreted as symbols of failure. Rather, they signal the dawning of a scientific revolution that holds the potential to fundamentally reshape our understanding of space, time, and humanity's role within the cosmos. The universe is proving to be far more intricate and astonishing than we ever dreamed possible. JWST hasn't indicated that our previous understandings are entirely wrong. Instead, it has illuminated the vast expanses of knowledge still awaiting exploration. This monumental advancement has not closed the chapter on our cosmic narrative. It has shown that we have merely skimmed the surface of its first page. If you found this exploration of the frontier of human knowledge enlightening and thought-provoking, we encourage you to share your insights in the comments below. We would love to hear your perspective. Thank you for joining us.